Hi everyone, my name is Nofel Yaseen and today I am presenting the work on how to find the sweet spot that balances the cost and quality of collecting network monitoring data. This work was done at Microsoft in collaboration with the University of Pennsylvania. This is a mini version of the data center topology where we have a few switches and a few clusters of servers. Over these servers and switches, we have protocols, lots and lots of different kinds of protocols. As we have many devices running many protocols interacting with many other devices, there is a potential of failures, and failures can happen everywhere. Failure reduces the availability of the network. So operators require granular monitoring to catch these failures. In our survey of measurements collected from many production monitoring systems of a large cloud provider, we observe operators typically choose to be on the safer side by collecting as much information as possible, subject to some arbitrary set of constraints. Operators cannot answer as to whether the chosen measurement rate is adequate for the given metric or whether measuring more or less frequently will lead to better insights. In fact, operators often express concern that collecting less information could lead to missing out on important insights. An operator collect information about lots of metrics, for example, CPU, memory, and link relation, and the list just goes on. Collection of such a large amount of data has a very high overhead. Let's see one example how we take the measurement. Here we are measuring how switch temperature changes with time. It is an important metric as large fluctuation increases the failure probability of the switch. We are constructing the graph on the left by taking frequent samples as the temperature changes with time. The red arrows indicate where we took the measurements in time. If we take frequent samples, we are able to interpret the data correctly. But if we do not take the measurements frequently, our interpretation of the underlying data is incorrect. We miss out on fluctuations that indicate higher probability of switch failure. Therefore, we ask an important question: how to guarantee we are sampling enough but not waste resources? Well, there is a theoretical concept in signal processing called Nyquist rate. Sampling above Nyquist rate enables us to recover the underlying data completely, and sampling below Nyquist rate causes aliasing or distortion. Visually, we have an original signal that is sampled by the monitor to get the sample data. The sample data is passed through a three-step process to reconstruct the signal. For in-depth understanding of the three-step process, please refer to the paper or a textbook such as Digital Signal Processing by Oppenheim. The important part is if the sampling rate of the monitor is above the Nyquist rate, the reconstructed signal is equal to the original signal. Otherwise, it is distorted. Here are a few examples of data reconstruction by sampling at different rates. If we sample above Nyquist rate, we can reconstruct the data exactly, and if we don't sample fast enough, we'll see distortion and our reconstruction would not match the original data. Now we know about ideal sampling rate. The question is, how can we sample a network at the Nyquist rate? We can consider the entire network as a set of digital signals. This figure is a summary of our observations showing that operators are significantly sampling above the Nyquist rate at a diverse set of metrics. Y-axis represents the fraction of devices that operators are oversampling. For each bar, the number of devices are in thousands. This indicates that many measurements at many devices could in fact be sampled far less frequently, resulting in significant reduction in monitoring cost without loss in information. This shows we can save a lot of resources. In practice, the Nyquist rate of devices is not constant at all times. During relatively static periods, a measurement may not change quickly, requiring a low sampling rate. However, during other periods, it may exhibit more dynamism, requiring a higher sampling rate. A practical system must therefore continuously analyze the measurements to determine whether the currently employed sampling rate is sufficient, that it is higher than the Nyquist rate. It must also be able to track changes in the Nyquist rate and adapt by changing how often measurements are performed. From the last two slides, we know there are lots of devices where the sampling rate is higher than the Nyquist rate, and Nyquist rate keeps on changing with time. One question is, how much can we actually save? Here we show a graph with average ratio of current sampling rate versus Nyquist rate. This is the amount of times by which we can reduce the monitoring for each metric. A caveat is that these savings are only possible if we are sampling at exactly the Nyquist rate. That is the optimal rate. Now I have told you about the Nyquist rate. The question is, how do we select the sampling rate at each time? There is also work in signal processing that recommends to sample at two different rates indicated by red and green arrows here. We pass both sample data through the three-step process. If both has the same output, we can stay or reduce the current sampling rate. If there's a difference, we keep increasing the sampling rate until we stop seeing aliasing or we have reached the maximum sampling rate. Here is an example of how the Nyquist rate of temperature data changes with time and how operators need to adapt the sampling rate. The y-axis represents the Nyquist rate, or in other words, the number of samples we need to take per second to get the correct representation of the underlying data. In conclusion, monitoring systems are a crucial part of ensuring high availability for data centers. Nyquist rate provides guidance for optimizing existing monitoring systems, and simply adapting the sampling rate also saves us a lot of resources. In this paper, we focused on monitoring systems that fit nicely into the Nyquist model of sampling. They periodically sample a numeric metric at a fixed frequency. However, there are complex systems that does measurements based on per packet events. One direction of future work is, can we apply the idea of Nyquist rate there? Then there are many applications that may monitor and use multiple different signals. The joint distribution of these signals may be important to such applications. As long as we sample each individual signal at a rate higher than Nyquist, we can recover the original signal. However, if the Nyquist rate of even one of the signal changes faster than we can adapt, we may lose correlation among signals. The Nyquist-Shannon theorem is one example of a technique from the realm of signal processing that can be applied to data centers. Future research needs to explore what other techniques can we borrow from signal processing. Thank you, and for any questions and comments, you can reach out to me on my email.